In this presentation, I'll be going over the ability of sulfaguanidine to form co-crystals with different coformers and how hydrogen bonding patterns could influence the overall crystal packing, as well as the methods of characterization like IR and X-ray diffraction that are used to confirm the hydrogen bonding existence. To prepare the co-crystals, the researchers used two methods. First was the slurry method, where sulfaguanidine and a coformer are mixed with a small amount of solvent until they crystallize together. The second was a slow evaporation method, where the solvent gradually evaporates and leaves behind the co-crystals. Using these techniques, the researchers successfully obtained 5 distinct co-crystals, each having its own unique hydrogen bonding arrangements. The figure in this slide shows the variety of coformers tested with sulfaguanidine. The structures highlighted in red are coformers that produce stable co-crystals, while the structures highlighted in black were unstable co-crystals, and the structures highlighted in blue were co-crystals used in previous findings. An example of the stable co-crystals is 4-nitrobenzoic acid, and it was successful because it had a carboxylic acid group that perfectly complemented the donors and acceptors of sulfaguanidine, which enabled the formation of strong and stable hydrogen bonds. An example of unstable co-crystals is 4-hydroxybenzoic acid. It was unsuccessful even though it had a carboxyl group because the weaker hydrogen bonding ability meant it couldn't compete with the strong donor and acceptor groups of sulfaguanidine, thereby not forming any stable co-crystals. The sulfaguanidine structure had two key functional groups, which were a guanidine group and a sulfonamide group. The figure in this slide shows both of those two groups, the guanidine group on the left and the sulfonamide group on the right. The guanidine group had multiple nitrogen-hydrogen bonds, which served as hydrogen bond donors. The sulfonamide group contained 2 oxygen atoms that served as strong hydrogen bond acceptors, and an amine group that could donate hydrogen bonds. The hydrogen bond interaction were very stable due to the hydrogen atoms being around 180 degrees between the donor and acceptors, making them linear. In sulfaguanidine crystals, the recurrent hydrogen bond motifs, where 2 donors and 2 acceptors form an 8-membered ring, is what stabilizes the overall crystal lattice. To confirm the hydrogen bonding, the researchers combined experimental and computational techniques. There are 2 figures in this graph, with the first one displaying IR spectroscopy, indicating different stretches and peaks of functional group presence in sulfaguanidine, and the second figure showing the structures of amino and the imino forms. IR spectroscopy showed shifts in the amines, imines, and sulfur dioxide stretching bands, which indicated that these groups were forming hydrogen bonds. Powder X-ray diffraction showed new peaks, also proving the formation of crystalline phases. Differential scanning calorimetry was also used to show the melting points were altered, which reflected a change in the stability. Single crystal data showed that the hydrogen bonds were linear and short in donor-acceptor distance, with bond angles approximately at 180 degrees. The large angles meant the donor, acceptor, and hydrogen atoms are aligned, maximizing orbital overlap and strengthening the interactions. Hirschfeld surface analysis and electrostatic potential mapping was also used to confirm which atoms were donors and which were receptors. In conclusion, sulfaguanidine forms hydrogen-bonded co-crystals with a variety of coformers. The crystal structures revealed common patterns that play a key role in the molecular packing. Experiments like IR and thermal analysis like the differential scanning calorimetry confirm how hydrogen bonding can be used to design new pharmaceutical co-crystals.